Hi everyone. Before we begin, if you can all please confirm that you can hear me and see the slides clearly by just typing in yes in the chat window. Great, perfect, thank you. I can see a number of replies. Please feel free to introduce yourself, your name, your position, company, and which country you belong to. It's great to see an international audience of people from all the industries and backgrounds. Great. Thank you so much, everyone, for joining in. It's really nice to meet you all. So I welcome you all to today's webinar on the significance of vibration measurement, analysis, and troubleshooting in piping systems. My name is Sayeda Samia Avez, and I am the lead software engineer at Velosi. For the next 2 hours, it will be our pleasure to host this webinar for you. We would like to thank you all for joining us today, and we hope that by the end of this webinar, you will have gained good knowledge about the subject. So as some of you may know that this is our 55th webinar in a series of technical webinars. We are conducting one webinar every second Saturday as a general practice. You can follow us on LinkedIn and make sure to check our website to stay tuned to the latest updates. Also, we upload our webinars on our YouTube channel, which is Velosi, so you can feel free to go and subscribe to the channel and watch our YouTube videos. So today, we have quite an experienced panel of speakers for the subject matter. I'm here with my colleagues, Mr. Ijazul Karim Rao, the Managing Director, Principal Integrity and Safety Consultant, Mr. Anthony James Williams, who is the General Manager, Global Sales, Mr. Imran Saeed, who is the Manager at RBI Department. So I can ensure that you are all in good hands today. During this webinar, we encourage you all to keep asking in questions in order to clear any kind of doubts that may arise with time to time. This will not only help you, but will also help many others who can usually have the same kind of doubts and questions. There's a Q&A window, so you can type in your queries in that window, and you will either receive a reply immediately in the Q&A window, or we will answer it live during our session. We will try to answer as much questions as possible within the session. Also, by the end of this session, we will have a detailed QA session. Please accept our apologies if your question is not addressed, because due to the high volume of questions that we usually receive in this given limited time, we have to be selective. We'll also be issuing a participation certificates to all those who have attended at least 80% of the webinar and have participated in the discussions during the Q&A session. So since this is quite a technical subject, and today we will be touching the key theoretical and practical aspects of the significance of vibration, measurement, analysis, and troubleshooting in piping systems in this limited time of 2 hours, we request you all to follow along with us and keep asking questions in order to help us in making this as engaging as possible. Today's webinar will involve a practical case study. Please note that the client name and data have been redacted. We will be following a practical approach. We'll walk you through the key steps through this case study. So before we begin, although most of us are in the comfort of our homes, we should be aware of the emergency exits. Due to the current COVID-19 situation and its emerging variants, we should be more careful, keep a safe distance, and in general, take care of ourselves and of those around us. So now I'll hand it over to our speaker for today, Mr. Ijazul Karim Rao, who will proceed with today's talk.
Assalamu alaikum and good day, everyone. I know there are various time zone in the various parts of the world. Today's topic would be presented jointly by myself and my colleague Mr. Imran Saeed. So I will be presenting the theoretical part or introductory part, and case study would be presented by Mr. Imran. So our discussion is mainly limited to the vibration measurement and analysis and troubleshooting of piping systems. We know that is a big subject if we have to cover rotary equipment, pumps and compressors. So that part is not being covered under this topic. That is basically explanation. So people should not have over expectation from this presentation. So general like introduction for the vibration of a piping system may be induced by internal pipe flow, like a fluid, high velocities, turbulent fluid, or there are multi-phase flows, single gas flow as well may cause some high pressure or high vibration. So the vibration which is induced by flow is called normally FIV, flow-induced vibration, and has a potential cause to damage the piping system. Vibration is an basically oscillatory motion about an equilibrium position. Consider a simple mass on a spring as shown in the basically this diagram. As a when like a pendulum or a spring is vibrating, so it is normal. The number of vibrations, the number of to and fro motions are measured by its natural frequency, and the formula of the natural frequency is 1/2 pi spring stiffness into mass, and where the resulting vibration can be defined in terms of displacement, velocity, or x. So their main causes of their common causes, I would say, not main, of the piping vibration, that flow is one of those. Then second one is the mechanical excitation. Mechanical excitation means there might be a rotating equipment associated with the piping system that may cause a vibration. Similarly, if there's a downstream of a downstream of a pressure reduction valve, that may also cause high excitation or vibration. Then pulsation is normally caused by the reciprocating pumps. Then high frequency acoustic excitation, that is basically if high velocity fluid is passing through the gas. Then surge momentum change due to valve operation. Surge means like if all of a sudden some valve is closed or pump is started or closed, and then or there could be two-phase flow as well, which may cause surge. Surge may also cause vibration. Cavitation is a mechanism which normally applies in the pumps when we have two-phase flow or the gas. Sorry, let's say if a liquid is supposed to be pumped by the pump, then if a gas goes inside the liquid, that may cause some cavitation. Bubbles and bubble burst may cause vibration as well. Flashing is a mechanism, as I earlier said, mechanical excitation area. Flashing means, for example, if a steam or a condensate is separated from a steam circuit, and there is a high pressure steam circuit from where the condensate is separated out, and when condensate is separated into low pressure circuit, it may flash again to the stream, and which may cause some high volume generation and then subsequent vibration. So some more details which I give little introduction. So flow induced vibration, turbulence will exist in most piping system encountered in practice. In straight pipe, it is generated by the turbulent boundary. Like turbulent boundary is like if any fluid which is passing more than 4,000 or 10,000 Reynolds number, and if the flow is below 2,000 Reynolds number, it could be laminar flow. In between 2,000 to 4,000 is a transient flow, and after 4,000 turbulence flow starts. So for most cases experienced in practice, the dominant source of turbulence are major flow discontinuities in the system. For example, there could be a valve, there could be a T, or there could be elbow, there could be a reducer. And typical examples are process equipment, partially closed valve, short radius or mitered bends, T's or reducers. Mechanical excitation, the most of the problems of the nature encountered have been associated with the reciprocating positive displacement compressors or pumps. Like the pumps and compressors are the source of this basically excitation. And the dynamic forces directly load the power connected to the machine. If machine would be vibrating due to whatever reason, and that could be, let's say, if there is a cavitation in the machine, or there could be a misalignment of the machine, or there could be other process reasons, and that would be machine is vibrating and the associated piping would also be vibrating as well. Normally, high levels of vibrations and failures only occur where the pipework system has a natural frequency of a multiple of running speed the machine. Like if the vibration is a lot more, vibration of the piping system is a lot more than the average vibration being measured by the machine itself. To ensure there is no coupling, the excitation frequencies, including harmonic, should not be within plus minus 20% of the structural natural frequencies of the pulsation. Is the same thing like reciprocating pumps or the pumps which are running by a piston. So may cause pulsation, like pulsation has the process is working. Pressure pulsation is a tonal form of excitation where dynamic pressure fluctuation are generated in the process fluid of discrete frequencies. The pressure pulsation results in dynamic force being applied at bends, reducers, and other changes of the sector. In some way, the structures exhibit natural frequencies. The fluid within piping system also exhibit acoustic natural frequencies. These are frequencies at which standing move pattern, wave pattern are established in the liquid or a gas. The next thing is high frequency acoustic excitation. A gas system, high level of high frequency acoustic energy can be generated by pressure reducing devices such as relief valves, control valves, or orifice plates. Acoustic fatigue is particular concern as it tends to affect safety of the plant. And normally, acoustic excitation normally occurs at high velocities, or we call it the particular terminology which is used to see if the sonic velocity range comes, or where the Mach number in the flare system or leaf system goes more than the acceptable range. So API 521 mainly try to cover this part of the excitation, mainly in the leaf system or in the condensate separation systems. If the time of a failure is short, typically a few minutes or hours, due to the high frequency response, as well as giving rise to the high tonal noise level explained in the pipe, this form of excitation can generally serve high frequency vibration in the piping systems. The vibration take the form of local pipe wall flexures, and this cause basically the more high vibration with the sound and cause the failure, and also create high noise. The high noise levels are generally generated by high velocity fluid impingements on the pipe wall, turbulence mixing, and for choked flow or the shock wave downstream of the flow restrictions. For example, when a PSV is lifted and the pressure at the upstream of the PSVs could be, let's say, 300 bar, but when PSV is lifted, the fluid would be entering to the relief system, and their pressure would be maximum, let's say, 5 bar, 2 bar, 3 bar. So the DP of 290 bar, or let's say 50 bar, 60 bar, very high differential pressure would be there, and this would be causing more acoustic excitation and the very high frequency due to sudden changes of these pressure reduction volume. Surge momentum changes due to valve operations. One is a valve operation. For example, if sudden closure or opening of a deluge valve or any isolation valve or motorized valve or control valve or ESD valve or BDV valve. So these are all type of valves which are used in certain emergencies, may cause certain surge in the system, and that surge may cause failure in the pipe. So in all installation of such valves is done with proper surge analysis, and the piping systems are designed to withstand the highest pressure which could be caused by that surge. And next point is high transit forces can also be generated by the rapid change in fluid momentum caused by the sudden opening or closing of the valve. This is what I basically explained. And the main issue is when you are trying to stop the fluid, it would be transmitting its pressure to some directions, and those directions should be in position to withstand with those high pressures and the torque which would be generated by those pressures. Cavitation is an issue which normally comes under, as I explained earlier, in the pumps, when pumps are managed designed to take care of liquids. If some gas or some bubbles goes with the liquid, and the bursting of those bubbles cause cavitation and high vibration in the centrifugal pumps or compressors. Then flashing is basically another way of cavitation, or as I explained earlier, is a main issue which normally goes with the mainly with the condensate system associated with the steam lines. There are three levels of steam: normal, low pressure steam, medium pressure steam, and superheated stream or high pressure stream. And all these three streams condensate is normally separated out by a steam traps or some other mechanisms. And when this high pressure condensate, when it goes to the low pressure condensate circuit, that condensate may flash again and become steam, and the volume of that steam is quite high as compared to the volume of the condensate which is supposed to be separated out, and this cause also very high velocities and cavitation, as well as the erosion corrosion problem in those circuits. So flashing is also one area which may cause high vibration and then subsequent high erosion corrosion. So typical vibration risk in a piping system, if you see a diagram here. So this is one of the pump or a compressor, you may say, mechanical excitation, or there could be a pulsation, which is at a subsequent valve, right? And then this structural discontinuities, like you can see there is a T here, and this is a relief system, relief load. Then SBC, small bore connection, could also be there. And dead leg pulsation means the bypass, if this also size is small. Then there could be a water hammer. Water hammer can take place in a steam system, and flashing can take place in basically condensate cell. The structural transitions, for example, if structural support is there, that if there is some sort of vibration or the structure is not fully locked, then it may also contribute to the vibration point of view. And there could be also spring hangers or flexible supports, which may contribute into high vibration as well. So when there is a piping fatigue, or there could be some vibration or fatigue related failures. So this is one of the example, like a fatigue crack shown by dip entry test in the T joint here. And on this elbow, welded joint fatigue crack, leakage could also occur. And this is also one of the example of the failure due to vibration or the fatigue caused by the vibration. So crane basically threading between two surfaces, there's also vibration or the to and flow motion. And if the pipe is directly resting on a structural support, so due to this to and flow motion, and if there's some condensate also available or water drops also available in that particular point, may cause a very high corrosion, which is called corrosion under support location. So similarly, there's crack due to fitting as well. Like if definition point of view, I would go again here. In addition to fatigue issues, vibration can result fretting occurs between two surfaces in contact subject to cyclic relative motion, resulting in one or both of the surface being worn away. So here this example is if a SS is welded with carbon steel or carbon steel is welded with SS. That may also cause various thermal movement, and that due to that thermal movement, it may cause it. Then piping vibration type point of view, like if the low frequency vibration, which is less than 100 hertz, medium frequency, less than 300, 100 to 300, we may say, broadband frequencies, then discrete single frequency, then high frequency vibrations, which are greater than 300 hertz. So then piping vibration types, for example, understanding of the piping vibration types is fundamental in order to have a better approach for conducting reliable vibration measurements, accurate assessment, and consequently the effective solutions. The vibration in a piping system can be classified based on vibration frequencies and overall levels, as we explained in the previous slide as well. Like low frequency, then is a high frequency, and the broadband and discrete single frequency. The four categories are there. So the same thing, like in the frequency in hertz point of view, and some companies like Saudi Aramco, they also have published a graph like what is the acceptable level of frequency depending upon the conditions. For example, if here vibration amplitude mills peak to peak value, right? And here is the frequency. Depends upon if the amplitude is lesser, then the high frequency is also acceptable. If amplitude is bigger, then if frequency side like could be bigger. If you can see that, like if the amplitude is this, then only lesser frequency is acceptable. However, if the amplitude is lower, then the level of frequency can go to up to 300. So then this area of concern and problematic area. So this is a normal screening graph which can be used to associate or to assess which piping system would be subject to vibration and vibration related defects, or which may not be. So this is the velocity severity chart. If you see it, it is again same, the velocity inches per second RMS on the vibration side, and then there is a frequency. And the same way, if velocity is lower, is acceptable, and if like RMS is increasing, the concern problem would be increasing as the frequency would be increasing. So piping vibration measurement guidelines, like how we can measure these vibrations. So the following are detailed measurement guidelines. Vibration measurement should be performed at the most severe vibration condition, which may require measurement at multiple operational conditions. Like first of all, like vibration measurement cannot be done when plant is not in operation. Number two, if there's a vibration at the same time, like at the clinical symptoms, when clinical symptoms are there, same time test should be conducted. So here, when vibration is taking place at that time, it should be measured. For mainline, uh, take vibration measurement at those locations perceived to have the highest vibration amplitude, right? Midspan, near valve, elbows, change in diameter, or like where the weak links are there, small bore connections are there, and where you expect more vibration. For small bore connections, a measurement should be performed at the end flange of the cantilever arrangement or dead leg. Utilize the piping asymmetric drawing and mark and label the measurement locations. Take data in the vertical and horizontal directions at each measurement location where necessary. Also take measurement in direction along with pipe axis like a longitudinal side. Ensure that the pipe surface temperature does not exceed the transducer allowable temperature. It should not be because your measuring tool like a probe is damaged due to high temperature of the piping system. It is critical to ensure that the transducer is firmly secured to the piping system, and it should also be compatible with the diameter of that particular pipe. For small bore piping, you may need to use like smaller size transistors, less than 50% of the pipe mass. Sometimes, for example, for small bore piping, UT probes are unable to fit. So normally you need to use micro probes for small dia. Similarly, for vibration measurement, compatibility of the probe with the pipe should be. So this is a diagram like how the location could be like a elbow or the upstream side, and it can be marked also like where 31 mils, 5 mils, various values are there. So we have to see what the highest value and how this like vibration may not be equal or same at every place. There could be a various level of vibration depending on the diameter and the location. The type of vibration measurement tools, like there are various tools are there. So we are not promoting any particular tool, but we are just saying what tool we have been using for this measurement. One is Fluke 805 FC vibration meter. So this tool can be used. And there is a Bentley's Nevada tools, which is also available, which is portable, and there are fixed tools as well. These are the portable tools can be used. Then standard and regulations which provide guidelines to identify these piping systems which are subject to vibration defects, and then how those vibration related defects should be arrested and monitored and prevented. For example, the main standard is Energy Institute guideline for avoidance of vibration induced fatigue failure in process pipe work. This is one. This is an international standard coming from European Union. Then there is a Saudi Aramco has also issued guidelines for setting acceptance, alarm, and shutdown vibration limits for the piping system as well there. Then in old days, no ADNOC is there, but we have with us ZEDCO, which is now ADNOC Offshore. ZEDCO Development Company maintenance techniques are also available and covering up to a certain extent for piping vibration as well. Then Takrir nowadays ADNOC refining. They also have Takrir asset integrity and liability manual. It covers the vibration limits of the piping systems as well. Then API 571, a damage mechanism affecting fixed piping in the refining industry, also have a damage mechanism related to vibration or vibration related fatigue. Then 581 and 580 and ASME B31.3 also covers vibration related fatigue and their management aspect. Similarly, for the excitation sources or regarding the pumps and compressors, API 618 is a provide guideline which is acceptable limits for the vibrations or the alignment. Then API 674 positive displacement pumps, their management point of view. There is a Shell DEP, which also cover pipe supports and taking care of the vibration and the piping behaviors. Then BS 7608 is a fatigue design and assessment of steel structure. So these are the standards. It's not the all standard we have referred. So we have given some introduction to the standard what we are used to use, but there could be other standards which we may not be having access or we may not have listed in this list as well. So this is not the only standard which could be used. There could be other guidelines as well, coming from, let's say, European Union and other international. So, like overview, just a heading point of view, Energy Institute, a guideline for the avoidance of vibration-induced fatigue failure in process pipe. So this is the standard for the people who may not be familiar with. So guideline for the avoidance of vibration-induced fatigue failure in process pipe work. This is the standard Energy Institute, and these are the basically the index or the topics what they are. So general introduction, and I'm unable to basically read it. Okay, yes, it's better there. I can do what's the answer. If you can help. So like basically if I go by it, is overview of the piping vibrations, then understanding like a
undertaking a protective assessment. Then the fourth section is the troubleshooting a vibration issue. Then the technical modules like the qualitative assessment, quantitative mainline, LOF assessment. Then for the small bore connections, LOF assessment. Then the qualitative assessment for the thermowell. Then the visual assessment for the piping, tubing. Then based on the measurement, the assessment for the mainline, small bore connection, thermowells, and then good design engineering practices. So these are the basically the table of
contents. Right. So there's a this document provide a public domain methodology to help minimize the risk of vibration-induced fatigue of process piping. It is intended for use by engineer with no prerequisite knowledge of vibration. Pipe work vibration is only superficially covered by standard design codes, and hence awareness of the problem among plant designers and operators is limited. It is intended that this document will be addressed. There is another standard which is the Ramco one, guideline for setting acceptance alarm and shutdown vibration limits. This is easy to use. Like here, this is the SAER 5659, the guideline for setting acceptance alarms and shutdown vibration. Basically, these are the Ramco internal guideline what they are using, and it also covers the definition, acceptance level, alarm level, then shutdown level. The various levels of alarms are there. The recommendation of the accepted vibration levels, and it is for the motors, for vertical motors, pumps, fin fan, gear unit, reciprocating machines, and similarly for the piping systems as well. So these are good documents as a good practice if we need to check the measurement of our equipment wherever you are working, and then whether that is acceptable, not acceptable, and accordingly the corrective action can be planned. So the purpose of this document is to lay down guidelines for acceptable alarm and shutdown vibration limit for existing rotating equipment and allowable piping and valve vibration levels throughout Saudi Aramco. This document is not applicable for establishing acceptance criteria for equipment like effective test or commissioning, or for setting alarm and shutdown criteria for monitoring and protective system of new equipment at new stage. But this is a good guideline what Saudi Aramco has developed for themselves. It is not for public, but since we are providing services, so we have access, and we are used to work on these documents as a service provider to Saudi Aramco. Similarly, we have given example of ADNOC standards. ADNOC also have given various guidelines, and similarly, Shell standards, DP is also there. BP has also given their guidelines. ExxonMobil has given their guidelines. So there are various guidelines are available if we would be aware. And last but not least, like Dragon Oil as well, they also developed their vibration measurement system limits, and how to manage those risks which are relevant to vibration of the static and piping equipments, and even rotary side as well. So the various companies are having these approaches, and it is simply very simple to follow, but homework is required, and certain actions are required to be taken. We have executed one project recently. The same case study we are presenting here is for the onshore and offshore, like a vibration risk assessment and survey for onshore and offshore production assets. So my colleague would be presenting, Mr. Imran Saeed, and in this, when I would be leaving, so we would be taking questions. Can you read the
one question? Is there any consideration of extend length for flashing to be accounted for screening the vibration?
See, when there's a flashing, it's always Joule-Thomson effect, or how the Due to pressure reduction of the condensate would be converting into the gas or vapors, that volume assessment is required to be measured and calculated or estimated. Then accordingly, either size of the downstream part is changed or the metallurgy of downstream piping system is changed to twin resistant alloys. These are the two solutions, and the volume assessment is important to be established.
Next question. On a reciprocating positive displacement pump, which one has more impact to piping vibration, plunger or diaphragm pump?
See, plunger would have more than diaphragm, because plunger is back and forth moving, whereas diaphragm is also similar part, but like in diaphragm, the suction is done and then discharge. Plunger also is less like a piston. So, but in piston side, there are more high pressure, and plunger side more high pressure as compared to diaphragm. Diaphragm works with a lower pressure range, generally.
Next question. What is the frequency limit of the piping natural frequency to be considered for further screening during initial stage of the design for each vibration types?
See, there are various ranges are given. I remember is a 20 hertz, but they will be coming back. I don't remember the exact range, but like 300 below, 300 above, and in between complex. And there are, I think, threshold limit of 20 hertz or lesser. We'll reconfirm as we go.
Question. Is there any standard available that indicates the allowable thickness of any pipe?
Allowable thicknesses are covered by ASME 31.4, 31.3, 31.1, 31.8. So these are the standard where design values are established by the pipe wall or hoop stress calculation, like a PD over SC normal formula is there, and that defines the allowable stress and allowable thicknesses under any required pressure.
Okay, last question. Do we analyze water hammering, pipe hammering using the same methodology as we analyze pipe vibration?
No. See, hammering calculation is different, right? Like a surge control or the effect of the surge or hammer on the piping system. The first thing is the process design is in place. So as when hammer is there, it means there will be two phases, and those two phases has to be separated out or minimized. So there's one cause. Like if a water hammer is taking place in steam, so in the steam circuit, the condensate should be separated out. And similarly, if there could be a two-phase liquid carrying gas, so in those pockets, gas may also create bubbles and then may cause some problems. In both ways, this issue is managed by process design in accordance with API 14E or applicable process practices. Okay, Mr. Imran.
Okay. Good day, gentlemen. So now we are in the second part of our presentation. So in this part of the presentation, we will discuss about a case study for the vibration risk assessment and survey for onshore and offshore production assets. So the project background, basically company has some raised issues which are related to the vibration induced fatigue within their piping facilities at onshore. Considering that risk, the company decided to perform the vibration risk assessment and the survey to undertake a risk analysis in order to identify the high risk items, and then for these high risk items the measurement should be taken by the vibration measurement, and then accordingly the mitigation plan or the recommendation to be provided in order to reduce the risk to the alarm as low as reasonably practicable. The objective of the project, as we mentioned from the background, that first we have to identify the lines which are applicable under the vibration issue. Then we have to perform the walk-down survey of the plant. You can say visual survey, dual inspection, then perform the vibration risk assessment and provide the recommendation for the mitigation. So the detailed scope of work that include but not limited to identify the piping, instrument tubing, structure elements or ancillary static equipment elements across the production facilities that represent an integrity threat due to the vibration induced fatigue, visual site survey, as well as the review of the document to identify, if any, potential vibration problems and poor installation and the design, plant defects from the original design intent, observe vibration problems on site, perform vibration risk assessment, preparation of the anomaly reports, provide recommendation for the mitigation of vibration threat, development of the vibration management strategy. So the assets that were covered under this like the case studies, these are the basically numbers are as an indicative purpose. So we covered this, we performed the assessment for the onshore and offshore facilities. In the onshore, there were 15 piping systems for the central processing facility. And for the offshore, there are the two production assets, 1 and 2, where around about 300 piping systems were covered under this project. The project deliverables, as mentioned in the scope of work and the objectives. First, we have to carry out the site survey. So site survey report, then vibration risk management strategy, vibration risk assessment report, and then the final presentation containing the various piping with threat due to vibration and their mitigation. So ultimate, you can say this one, the goal is we need to identify the piping which have these vibration issues, then based on these vibration issues, the risk assessment, and then the piping which are at a high risk for those piping systems, the mitigation plan as the recommendation. The tool which we use for this study in order to carry out the survey at the site, we use the Fluke 805 FC vibration meter. This equipment was used for the vibration measurement. There are the other tools also available which we have mentioned in our previous slides, but for this project we basically use this one, the Fluke 805. This is the technical specifications for this equipment. If you will see this one from the vibration meter with respect to the frequency, this equipment can work from 10 Hz to 1000 Hz with the low frequency, whereas in the high frequency it can work up to the 20,000 Hz, and the vibration limit is 50 GP to 100 GP, signal 80 dB, and so within the high frequency it can work up to the, you can say that 20,000 Hz to the 80,000, and then the amplitude units, infrared thermometer. So these are basically the technical specifications for this equipment. So the first vibration tool setup that we carried out in order to perform the survey. So this is basically the people who want to use this tool to carry out the to take the measurement, that what is the procedure in order to set up the tool, although the guidelines are the, you can say the manual would be available. So these are the basically the steps how to use this equipment in order to get the accurate measurements or the readings. Then whatever the data that have been you can say that we have taken from this equipment or the tool, that can be exported and trends into the trends you can see on your screen. The trends can be made, it can be exported into the Excel. Then based on the Excel we can use this readings for our assessment as per the Energy Institute guideline. So this is the overall approach. If you will see this one, the approach which we followed, like the first, as per any study, we need to collect the data with data validation. If any data is missing, that data collected. Then the first step, if you people remember that when we were in the technical part of this presentation or webinar, so as a first step, identification of the vibration excitation source. What are the vibration excitation source from where the vibration is produced, and then the visual assessment or the vibration measurement survey. So as a first step, the visual assessment would be carried out. Then for those, you can say the identifications at those locations, the measurements, then the classification of the piping as per the criteria, results and recommendations, preparation of the anomaly reports for those piping systems which are not in the acceptable range, for those piping, the anomaly reports, and then there will be a workshop where all these issues would be discussed and finalized. So as part of the this assessment, so the data that was collected or the data that is required, it is you can say that the main data consists of P&IDs, PFTs, equipment, process data sheet, piping isometric drawings, then the general knowledge of the facility, equipment general arrangement drawings, control valve, calculations, valve data sheets, line designation tables, plant description, process description, operating manual, piping specification. This is basically the not all data, but the minimum element are the mandatory data elements required that have been mentioned on this screen. This is the data status that we have collected. Initially, after the data collection, the data status were prepared and submitted, like what data that have been collected. After the collection of the data, so if you people remember that one, our scope was there are the 3 facilities, one onshore and there are the 2 offshore facilities. So based on the different documents that have been collected from the, you can say, the client, the asset register was 12. In the asset register, all the engineering data and the required data that is required for the vibration risk assessment study have been extracted and populated into this asset register, which is basically the main engineering data, the operational data, then the vibration risk. So if you will see this one, for any piping, like these are the piping tag number on any facility. Then we identify from and to position of the piping, the PM pipe size, pipe class, piping design code, the base material. Then what is the pipe schedule, the nominal thickness, corrosion allowance, design and operating pressure, temperature, minimum, maximum pressure. What is the fluid content? Because the fluid content is also required if there is a 2-phase flow or single phase flow that we need to consider. Then what is the mass flow rate for the fluids, oil, gas, if you can say this one, the oil, water, and then mass flow rate for the gas if it is a multi-phase fluid. After the preparation of the asset register, the second step, which is the important step for the vibration risk assessment, is the identification of the excitation source. If you remember that one, in our presentation in the technical part, we have mentioned the different vibration excitation sources. So based on the review of the P&IDs and the other documents, we have identified those excitation sources, and then for those excitation sources, the qualitative assessment was carried out. So the sources would be flow-induced turbulence, flow-induced pulsation, high-frequency acoustic excitation, mechanical excitation, pulsation, rotating stall excitation, cavitation and flashing excitation, surge, momentum changing excitation, vortex shedding, and the sludge flow excitation. These are the different excitation sources that we have identified from the P&IDs. If you will see this one on this drawing, so for example, those sources have been identified for a vessel, like wherever there is a control valve, the lines which are going to the flares. And if you will see on the bottom, then we have basically these lines were identified, marked with a different colors, the lines which are associated with the pressure control valve. There is change in the pressure, like sudden change, with a yellow color, the line with the thermo valve, blue color, then the level control valve, the like pink color, PCV. So there are the different excitation source that have been identified, and they have been marked with a different colors. So as the first step, the excitation source were identified from the P&IDs. Sorry, just 1 minute. After that one, after the identification of the excitation source, then at the you can say the facility, the walkthrough or the survey, first the visual survey, the physical examination of these piping are the locations that have been identified. The physical survey was carried out visual. Physical examine the identified piping system to determine the severity of the vibration problem. Note the location where the vibrations are the maximum, since these will be the proper point to mark the vibration measurement for use during the survey. So after the identification, the first step, you can say visual inspection of the walkthrough was carried out, where the exact vibration, like the location where we have the issues, so that those locations have been identified. Then only on those locations the measurements were carried out, so that one we can check the frequency, peak to peak, and the velocity, so that it can be further assessed the likelihood of the failure. Generally, falling points are observed, which will indicate the potential points. Failed piping with the fatigue cracks, high visual vibration, line movements, damage or ineffective sports and restraints, high vibration of the connected apparatuses, high impact or flow excited noise, proximity to the potential exciting source, for example, the pressure safety valves, any fast acting valve like emergency shutdown valves, blow down valves. General condition of the piping, like excessive corrosion, has a significant effect on fatigue endurance levels. Condition of the mainline sports. So these are the main points which were like checked during the walkthrough, and these are the critical locations from the vibration risk assessment point of view. The checklist was prepared. So like initially at the top, if you will see this one, this is the line designation number. So that line number, the condition, what is the design pressure, temperature, from and to the service. Either then, like these are the questionnaire, when the piping vibration first observed, was there any operational changes, then these need to be specifically. Then the type of the vibration, design, rotating equipment, if you can say the excitation source is from the rotating equipment, either any pump or the compressors that have been noted down as part of this one, the checklist. Similarly, the valves, like if the excitation source is from the valves, is the vibration near a control valve? If yes, then monitor the valve control behavior, throttling. If the valve creating slamming noise, and then the sporting with respect to the sports, which are basically at the design stage based on the vibration, like which is like the mitigation point of view, the sports which have been installed, what is their condition? Is there any Filmacy sport, check sports, anchor bolts, stud bolt, U-bolt condition, in order to check that there will be no loose bolt or the bolts are not missed. Is there a spring sport hanger in the system? If yes, then inspect its condition and check the below. Is the load indicator on the working range? Is the travel stop lock removed? So these are the basically the checklist that we have prepared, and during the walkthrough, the people they filled, and after that one the exact locations were identified where the measurement was carried out. So detailed measurement survey was carried out after the walkthrough, in which detailed vibration survey was carried out, comprised a review of the lines identified on the P&IDs, visual inspection, vibration velocity measurement. During the vibration measurements, there were some key findings, like we have just mentioned as a reference. Due to the sludge flow, 30-inch line is susceptible to the hammering and flow-induced vibration. So as you people remember that when there was a sludge flow was also one of the cause for the FIV. High noise was observed in the flare lines. Possibility of fretting damage due to the contact of the line with the flame arrestor and continuous vibration. So if you people remember that when these are linked, as we have described in our technical, like what will be the reasons. So for these vibration reasons, if you will see somewhere the high noise observed, somewhere the possibility of the fretting damage due to the contact of the line with the flame arrestor. Then as part of the visual inspection, physical examination of the identified excitation source to check for high vibration, noise, fretting damage, pipe geometry, anchor sports, clamp and pipe port damages. Mark of the location where excitation mechanism was evident, and the identification of the damaged pipe sports. As part of the visual inspection, some findings are like visual inspection confirmed inadequate sports for the pump tubing in upper and lower deck. This could result in the vibration-related failure of the piping of the concern. Visual inspection confirmed inadequate sports for suction tubing of a one pump, which in turn vibrates the concerned piping in a high-risk
zone. This could result in a vibration-related failure of the concerned piping. Visual inspection confirmed that no pipe ports at the elbow has been installed and other pipe ports are not effective due to the air gap and poor installation. This could result in a vibration-related failure of the concerned piping. So these are, you can see this one as a visual inspection. Some photographs has been taken where you can see that like for a 14-inch line, there were the damaged ports, and due to these the damaged ports, there were the issues in the vibration-related issues. This is the one like for the outlet of the manifold port damage observed. The damage insulation after the visual inspection and the survey, the vibration survey was carried out in which there is a one part like the vibration velocity measurement. So measurements were taken where the vibration was evident in high flow conditions. Time and date was also recorded. Measurement was taken at the X, Y, and Z coordinates, and highest value was taken for the assessment. So if you remember that one, for any points in a one isometric line, we mentioned that at a different point there will be a different like the values. So on the particular point, what will be the highest value measurement that have been taken for our assessment? Measurement locations were marked on the P&IDs. Sketches were prepared for the lines not found on the P&IDs, and you can say this one that their isometric drawings were built so that on the isometric drawings, the locations can be further marked. Vibration velocity and the frequency were assessed as per the guideline defined in the Energy Institute guideline for the vibration-induced fatigue, and there was a one methodology that was also developed by the Velosi. So if you will see this one, these are the locations, we marked up the locations, the small bore connection, 1, 2. There are the different where we have taken the reading, the numbers were mentioned. So in this way, on the P&IDs, all the locations were identified. Then the isometric drawings were marked, and on these isometric drawings, these locations were identified where the vibration measurement were taken. Then as per this vibration measurement, by using the Energy Institute guideline, there was a one graph, if you people remember that one, where with respect to the frequency and the velocity, we have the three criteria: acceptable, problem, and the concern. If the velocity is the less, even at a high vibration, we are in acceptable range. If the velocity is high and with a low frequency, we are in a problematic area. If you will see this one, at this particular point, the velocity was 27.13 high velocity. The vibration was even less, 12 hertz, but it was into the problematic zone. Whereas on the other area, you will see this one, like in one area, the frequency was 27 hertz, but velocity was less, 1.57, so which are in the acceptable range. So the velocity is important parameter. At high velocity, low frequency, that can cause the problem or the concern. At low velocity, even with a high frequency, we will be in a acceptable range as per the Energy Institute guideline. Then also you can say this one, with respect to the different measurements, the different piping which are in the concern area where the velocity was between 5 to 12, even the vibration was less than the 20, we were in the concern area, and more velocity 32, 37 with a less frequency 14 or 11 hertz in the problematic. The lines have been classified as a problematic. This is the graph which is on the screen. It's as per the Energy Institute guideline, where with respect to the frequency, hertz, and the velocity, like we have in a zone, acceptable, concern, and the problem. If you will see in this one, the graph with a low frequency, with a low velocity, like up to 1 to 2, even with a frequency 300 up to the 300, we are in acceptable zone. When the velocity will be coming high at the low vibration or low frequency, we will be in the concern or in the problematic zone. If you will see this one, if the velocity would be like greater than the 10, and frequency less than the 10, we will be in a problem. Whereas in the case of the low velocity, if the velocity is 1 or 2 and at the frequency of the 300 hertz, we are still in an acceptable range. If the vibration will become like greater than the 300, then in this one, like the advanced study or the further study to be carried out for the mitigation, like from the design point of view. This is the classification, when we put measure the assessment was after the identification, walkthrough, then the measurement was carried out. Then based on the measurement, we have classified the pipings into the three acceptable, concern, and the problem. So overall, there were the 6 piping that were in the problematic, 24 in a concern, and 178 in a acceptable. So these are basically like a indicative purpose in this case study. Same are represented in a graphic in a pie chart view. 3% fall in a high, 12% in a concern, and 85% in an acceptable range. Afterwards, the anomaly reports were prepared for the piping which were in a concern and the problem range, so that the mitigations can be provided or the recommendations can be provided. Detail of anomaly, fault, and recommendation are presented in the anomaly report. So there are the few recommendations, like design and installation of the pipe ports on the main lines of the concern, design and installation of the 2-plane bolted brace on the small bore connections, reinstate missing sports that were originally installed on the piping of the concern, shimming of the existing sports, installation of the resilient pad liner between the pipe clamps and the piping, modification and other maintenance work on the tubing. So these are the basically the anomaly reports where on the pictures were taken, then on the locations where the high vibration was measured, I've noted their location was mentioned. Then we mentioned that's like the small bore connection, then the location, like this section line. The anomaly reports were prepared, which represent the line number, the PNID, when the date was assessed, the anomaly fault, like the mechanical excitation, visual inspection confirms inadequate sports for the mentioned pipe, and pipe is vibrating within the problem zone. Then the recommendations, as we mentioned in the in the previous, increase the sports to main line by design and installation of the suitable sports according to the need. Resting sport, pipe guide sports, anchor clamps could be used. Maintenance activities such as shimming, reinstating missing sports, or the replacement of the damaged sports need to be carried out accordingly as per the requirement. This is basically the overall summary of the anomaly report. Like the data, the different anomaly reports were prepared, like the anomaly report number, the type, for which tag number, where the anomaly observed, on P&IDs, then the recommendation, there is another recommendation like rerun the hydraulic calculation at a current and actual flow rate to analyze the slugging at the finger tight sludge catcher area. Then there was some replacement for the valves. Add or replace the ball valve at PSV bypass line with the globe valve to regulate the flow. In the offshore production asset, total 31 readings were taken on the 17 lines, and then accordingly these lines were classified into these areas like acceptable, concern, and the problematic. And there are the 17 lines, they fall in a acceptable range. All the piping sports should be visually inspected to check for high vibration noise, fretting damage, pipe geometry, anchor sports and clamps, and pipe sports. Whereas on the another asset, total 468 readings were taken for the 176 lines. The 23 piping tubing, they were in a concern area and 5 were in a problem range. Total 13 anomaly reports were generated for these tags where immediate recommendations were given for the piping which were in the problem area, in the problematic zone. These 13 anomaly reports are combined for all piping tags in upper deck, which is due to the inadequate sports of the pump suction line and the outlet tubing. So for another facility, you can say at the onshore, total 83 readings were taken for the 15 line. And as per the criteria which we discussed earlier, that with respect to the frequency, velocity, on one piping tubing was in a concern and one in a problem range. 4 anomaly reports were generated, out of which one for 13-inch trunk line, 2 for the small bore connections. Then, as in each anomaly reports, recommendations and mitigation were provided in order to reduce the risk. So now we will take the few questions.
For the first question, how is the tear off happened when it is in the middle of the pipe? Tear off.
How is the
How it is the tear off happen when it is in the middle of the pipe?
if you people remember that one, somewhere in the inadequate sports or also due to the flow, like the length of the piping, then we need to basically carry out what is the you can say that velocity, sonic velocity, and we need to calculate the Reynolds number. Then accordingly, it will be like either it will be in the turbulent flow or transit flow.
Next question. Can vibrations be controlled by changing elastic material?
You can say this one as if you remember that one at the start. My colleague Ms. Rijaz has clearly mentioned that if there be in some areas some issues where you can say this one you cannot control or manage these issues, then by the engineering design or upgrading the material that can be minimized.
During piping vibration measurements, what will happen if the pipe surface temperature exceed the transducer allowable temperature?
If you will see this one, if the temperature will not be like in the range of this on the equipment, we need to calculate the temperature. My Ms. Anand, you can answer that one day because he was a.
During the Fluke 305, there is an option in the equipment. We can calculate in the temperature as well as in this equipment. So based on that, we can take the measurement on the highest temperature area.
Next question. What should be the ideal location to measure vibrations during the site assessment?
Site assessment.
During the,
Ideal location.
can you just repeat the question?
What should be the ideal location to measure vibration during site assessment?
During site, we have basically mentioned like we have to identify the location, identify the pipe. First, you have to do perform the site survey. Then, according to the site survey, you need to identify like which areas which are near the vibration. You can say where the excitation source available. Then, accordingly, you need to identify where there is a change in the flow direction. The areas which are like the downstream of the any control valve, where there is a change, sudden change in the pressure, sudden change in a flow. Those areas are basically the critical areas or location.
Next question. What is the main source of vibration in reciprocating or positive displacement pump?
A pump discharge where you have the high pressure, like that will be the main. If you remember that one in the we mentioned in one like I said drawing sheet where we mentioned that the discharge of the pump that will be the main type source. We can take one or two more questions and then we can.
Okay, next question. How can visual inspection tell us about the insufficient piping support or inadequate design?
You can see this one. Initially, you can say the piping isometric drawing. You have the piping sports that they have mentioned. Then by the walkthrough, you need to confirm that either these piping sports have been installed or not installed. And then by the you can say when you be at the field walkthrough, if you will observe any vibration issues, then you need to correlate it with respect to the as-built document, like from the isometric drawings and the physical condition, like either all the sports are installed or inadequate. Then you can say this one. In this way, you can from the physical survey you can identify.
Next question. High velocity with low frequency has a concern. In some vibration types, concern will be on high frequency phase rather than frequency in lower side. Can we consider the graph presented for only FIV and not for other vibration?
This graph is for the FIV. If you will see this one, this graph represents the two, like the frequency and the velocity. Like then based on this one, you can identify the areas. Similarly, if I will go back to our presentation at the start, we mentioned the two graphs as per the Energy Institute guideline. Like one is the frequency and velocity, second is the vibration peak to peak. Based on that one, with respect to the vibration, the frequency and vibration peak to peak value, you can correlate, you can check that one. So if you will see this one, from the velocity up to you can say that 1 inch per second, even at a 300 frequency, which is basically into high vibration, high frequency 300, you are in acceptable range. Whenever there be the velocity will be increased, this is basically for all type of the fluid flow, the velocity will increase from the certain range. At even low frequency, you will be in the problem. For example, you have a velocity of the 1 greater than 1, but the frequency is 10, you will be in a problem. You can say this one here, if you will see this one, the upper part, all this area, even with the low frequency, you are in a problem with the high velocity. Low velocity with the high frequency, you are in acceptable range.
If piping is attached in storage tank, what standard is it followed in vibration analysis? Is it tank standard, example API 650 or 620, or piping standard?
For the piping standard would be applicable from the design point of view, and then for the vibration, you need to basically follow the standard as we mentioned, basically the Energy Institute guideline, then other standards. These API 571 or the other, they will tell you about the damage. The last question, then we will finish. So the other question we can, whatever the question remaining, if there is any, then we can send them we will write them. So, okay, gentlemen, thank you very much for the people for the attending this session.